So we come to what I believe is the last video of the year, and that is Vesper Theory. And I'm covering much of what was explained in the last video. The only thing that I'm adding to it is the polarity of the molecule, meaning whether something is polar or nonpolar. Okay? If something is symmetrical, it is nonpolar. If something is asymmetrical, it is polar. Okay, so we'll get to that at the end, but I just thought I'd give you the two definitions in the beginning. So Vesper theory helps us determine the shapes of molecules. And the reason why we are so concerned about the shapes of molecules is because the shape of a molecule determines its behavior. So in other words, it's the shape of the molecule that tells me whether or not it's going to be dense or not dense. The shape tells me whether it's going to be a gas, a liquid, or a solid. The shape of the molecule tells me whether it's going to conduct electricity or not. The shape of the molecule tells me the density of the solid. So much of the properties of the molecule depend on its shape, and that's why we care so much about finding the shape of it. And so there's a process to finding the shape. First thing you have to do is the Lewis dot. Once you know the Lewis dot structure, then you find the hybridization. And then once you know the hybridization, you determine the shape. And from the shape, you determine the polarity. Okay? And then again, that determines the properties of the molecule. Okay? So let's get to it. Let's give an example. You already know how to do 1 and 2. That's the difficult part. 3 and 4 is the easy part. All right? I'm having trouble getting a new page. Let's do this. Let's go back. All right. So let's start off with something sort of simple, one that we've already done. Let's do boron chloride. So first you do the Lewis dot structure. Boron starts with three valence electrons, Y, because it's in group 3A. Chlorine starts with 7, because it's in group 7A. Okay. And you do your Lewis dot structure. Elements in group 3A follow the rule of 6, and elements in group 7A follow the rule of 8. Okay? Then we draw the shape. Okay? So we want to draw a three-dimensional shape. That's what I mean by shape. We want to know what it is in 3 dimensions. And in order to do that, we need to know the hybridization on that central boron. This is a non-three-dimensional shape. Okay? And in the last video I said you count up the number of things that are attached to it, and that tells you the hybridization. So since there are 3 things attached, the hybridization is going to be sp2, because 1 plus 2 equals 3. Okay? But we don't write the number 1, we just put a 2 there. Now to find the shape, you go to Appendix G, or you can use the book. There are diagrams in the book. So on Appendix G, you see this diagram. And so I go look for should get a different color here. There we go. So I looked for my hybridization, sp2. So that means my answer must either be this or this when it comes to shape. Either my shape will be trigonal or my shape will be angular. So how many atoms were attached to my boron? So if I go back, there's 1, 2, 3 atoms attached. So in my picture, I've got 1, 2, 3 atoms attached. So that means my answer would be trigonal, and that would be the shape of my molecule. Okay? So drawing it in 3 dimensions, it would look like this. Okay? The other way I could draw it would be a wedge coming out at you is coming out of the board, a dashed wedge behind is going behind, and the angle between all of these is going to be 120 degrees. So this is a 3-dimensional drawing of boron trichloride. Now, is it symmetrical? When you look at symmetry, you have to chop it down a bond line. So these 2 sides are symmetrical. These 2 sides are symmetrical. These 2 sides are symmetrical. So you're only allowed to chop it down a bond length, okay? You're not allowed to do something like this. Obviously that's not symmetrical, but you're not chopping it down a bond length. So because this is symmetrical, it means that my molecule is non-polar. Okay? All right? So let me just show you this in a 3-dimensional atom program. So I want to add 3 atoms to this, okay? And then I can move this thing around in 3 dimensions. You can see that all 3 atoms are in the same plane, and that the angle is 120 degrees, okay? Oops. All right, let's do methane. Methane is has a Lewis dot structure of this. Carbon is in group 4A, so it starts with 4, but it needs 8 around it. The hybridization, there are 4 atoms attached to this thing. So that means my hybridization is going to be sp3, okay? Now, this picture that I've drawn here, that's not a 3-dimensional picture, that's 2-dimensional. So we need to draw a 3-dimensional picture, and in order to do it, we need to know the hybridization, okay? So either you can look in your book or go to Appendix G. And now our hybridization is sp3, which means we have 3 choices. Either it's tetrahedral, pyramidal, or angular. So we have to ask ourselves how many atoms are attached. A solid circle means an atom. A circle with 2 dots means a lone pair of electrons, and we'll do an example of that one next. So the one that's got 4 atoms is tetrahedral, okay? So now we need to draw that, and I'm going to show you what it looks like. When we go to 4 atoms, there you go. You can see that none of the atoms have an angle of 90 degrees. In fact, on the bottom of the screen it shows that the angle is 109.47. My molecule is symmetrical. No matter how I move it in space, it always gives me symmetry. Okay? So let's draw this in 3 dimensions. It takes a little practice. You have one atom going above, one atom coming out at you, one atom going behind, and one atom over here. And the angle is 109. It is symmetrical, and therefore it is non-polar. Okay? So now let's do one that is asymmetrical. And what we're basically going to do is we're going to take one of these hydrogens and get rid of it, okay, and do something with just 3 atoms. And the classic example of this is ammonia, right? So nitrogen starts with 5 electrons. It needs to get 8. All right? And then when we draw it in 2 dimensions, there are 4 things attached to it still. 1, 2, 3, and this lone pair counts as the 4th thing attached to it. So we have 4 things attached. So the hybridization is the same as above, sp3, okay, as we did with the ammonia, with the methane. It was sp3. So even though it's not 4 atoms, it is still 4 things. So my hybridization is sp3. We then go to the appendix G. We are still in sp3, which means we have 1, 2, 3 choices. But we don't have 4 atoms, but we do have 3 atoms and 1 lone pair. So the correct shape is going to be pyramidal. So what does this look like in 3 dimensions? So this is what it looked like when you had 3 atoms, but now when you have, this is what it looked like when you had 4 atoms, but now let's remove one of the atoms and replace it with a lone pair of electrons. So now this is what you have. Now if you look at it like this, obviously that is not symmetrical. The right side is not symmetrical to the left side. And all you have to do is find one plane of asymmetry, and it's no longer symmetrical. So the name of this thing is it makes a little pyramid. So we call it pyramidal because it makes a pyramid. I'm just going to show you that's all right. So if we go back, we try to draw it. So like methane, so the lone pair, this has got negative charge. So that negative charge pushes the atoms away from it. And so what happens is the hydrogens become closer together, and the bond angle is 107. Now, knowing that number is not important. What is important is realizing what happens to that angle. If we go back up here, when we were symmetrical, the angle was 109.5. When the atom got replaced with a lone pair, it pushes the other atoms closer together, and therefore the angle gets smaller. Okay? This is asymmetrical, and therefore it is polar. Okay? Polar means that one side of the molecule is different than the other side. Poles mean opposites. Okay? So since there are electrons on this side of the molecule looks negative. And we have a fancy Greek letter for it. It's called lowercase delta. We say it's got a partial negative. Okay? The other side of the molecule looks like a partial positive. Because if one side's negative, the other side must be positive. Okay? So we do that. All right? Let's do a few more examples of these. Let's do water. Okay? So water is got this Lewis dot structure. Oxygen is in group 6A. So it starts with 6 electrons. Hydrogen follows the rule of 2. Oxygen follows the rule of 8. Okay? So in 2 dimensions, my molecule looks like this. And I count the number of things attached to it. 1, 2, 3, 4. Lone pairs count as something. So if there are 4 things attached, it means my hybridization is sp3. So now we go to Appendix G to find the 3-dimensional shape. And again, those shapes are also in your book. So how many things are attached? That's right, 4. So when I look at Appendix G, another way you can look at this is there's the number 4. So my hybridization is sp3. So I've got 3 options: tetrahedral, pyramidal, or angular. Well, which one has 2 atoms and 2 lone pairs? So my answer is angular. So what happens when I take away another atom and replace it with a lone pair? Okay? So now what you're left with are 2 lone pairs and 2 atoms, and if I take away the lone pairs, if I just hide them from view, oops, if I take away the lone pairs, they're still there, you just can't see them. All you have is left with an angle. And what is the angle? 105 degrees. Okay? So for water, you have 2 lone pairs, and then both of these lone pairs push the hydrogens closer together, and so then the bond angle becomes 105. Okay? So what is happening to the angle as we add lone pairs? It started at 109, then it went down to 107 from 1 lone pair, and then 2 lone pairs and went down to 105. And that's where you get the name of this thing called valence shell electron pair repulsion. Pairs of electrons repel the other atoms closer together. All right? Because there are electrons on this side, this side of the molecule has a partial negative. This side would have a partial positive, okay? So why am I using the word partial? Because when I write the formula for water out, you don't see any charges anywhere, okay? Water is a neutral molecule, okay? Water is neutral. Sodium chloride, on the other hand, is not a neutral molecule. It is a +1 and a -1. This thing is ionic. Remember when we did this? The chlorine steals the electron. And it actually becomes negative. The sodium becomes positive. So these things have actual charges, but you don't see that above the H and the O. This thing is neutral. However, this side of the molecule behaves as if it's negative because of the lone pairs of the electrons. And this side of the molecule behaves as if it's positive. So we say they have a partial negative and a partial positive. Okay? And this is very, very, very important if you are going to study biochemistry, the body. It is these polar bonds which makes the chemistry of life possible, because covalent bonds like that are very strong. Okay? Actually, I think I will make one short video about the importance of these bonds, because it really is really, really important. So, and I promised I wanted to get one more example, and this video is getting long enough as it is. Okay, so let's do a really complicated one, and let's do SF4. Okay, so sometimes things violate their rules. Okay, so sulfur usually follows the rule of 8 or the rule of 12. In this case, the sulfur is going to follow the rule of 10. And so you kind of have to be told this. So the sulfur starts off with its 6 because it's in group 6A. And then fluorine wants to get 8. So there's 8 there, 8 there. That fluorine's got 8. This fluorine has 8. Okay, and the sulfur ends up with 10 in this case. So if I were to draw this two-dimensionally, and have this, but how many things are attached to it? 1, 2, 3, 4, 5. Okay? So if I have 5 things attached, my hybridization would be sp3d, because 1 plus 1 plus 1 is 5. Okay? So, or you could just say, okay, I got 5 things attached to it. Let's go to Appendix G. Here's the number 5. Now I have 4 options for my answer. Which one of them has 4 atoms and 1 lone pair? And it's this one. Okay, and there's my 1 lone pair. So my answer is distorted tetrahedron. And you'll be using something like this. So 5 atoms, 1 lone pair. So this is what it looks like. 4 atoms, 1, 2, 3. Whoa! This one is also called a seesaw, as you can probably see right now why it's called a seesaw. Whoops. There's your there it looks like a seesaw. So there are 4 atoms, 1 lone pair. This thing is not symmetrical because one side of the molecule looks different. One side's got a lone pair, the other side does not. So we have to draw this in 3 dimensions. And you'll notice how the top and the bottom are slightly bent, and those angles are slightly bent. So if I were to draw this out of my sulfur, I got 1 fluorine above, 1 fluorine below, 1 fluorine over here, and 1 fluorine over there. Now my lone pair of electrons is here. That pushes everything closer together. So that means this fluorine goes in this way a little bit. This fluorine goes that way a little bit. These other 2 fluorines get bent closer together. Okay? And there you go. All right, so obviously if I chop this thing down that line, you don't get symmetry. Okay? So this one is asymmetrical and therefore polar. Okay? Now I'm just going to let you in on a little hint, is when you go look at Appendix G, all of these are polar. These 2 are nonpolar, and all of these on the outside are nonpolar. Okay? So that's one way you can remember it. All right, and thank you very much, and I will make one more video.